So in the last couple of videos, we had to come up with a formula with n and use limits in order to determine if the series converged or diverged. Now we're going to look at ways in order to figure that out without doing that for ones that are not, it's not possible to make that formula. So we know that if an infinite series converges, then of this type, where we're just adding terms together, the limit as n approaches infinity of that is equal to 0. That does not work the other way around. So we can't use that to determine if a series converges. We know if a series converges that this is equal to 0, but if it's equal to 0, we can't use that to say that if it converges, it could converge or diverge. But what we can do is we can use that idea to show that if it does not equal to 0, that it diverges. So see, these are some examples here. Since the limit as n approaches infinity of a sub n is 87, because it's 87 all the time here, that doesn't equal 0, and therefore that series diverges. This one here, we're adding the numbers from 1 to infinity, so the limit as n approaches infinity of n is infinity. So that one also diverges. This one doesn't exist because we're oscillating back and forth between 1 and -1. So the limit doesn't exist, which means it doesn't equal 0, which means that the series diverges. And this one also continues on to infinity, doesn't equal 0, and therefore that diverges. So we can say that if the limit as n approaches 0 of a sub n, or n approaches infinity of a sub n, does not equal 0, the series diverges. But if it does equal 0, then we can't use that to determine whether it converges or diverges. It could do either one still. So we can use the idea that if we have series that are identical after certain terms and we know that one of them converges or diverges, we can say the other one does also. And if they both converge, we know that they converge, but we don't know what the sum is. We can't assume that it's the same sum. So for most of the examples in this video that you're going to see, we're not going to calculate what the sum is. The idea here is really more to figure out whether the series converges or diverges. And so that's what we're going to be doing for these. So these are different theorems, and again, these will look very familiar to you. They're those properties of limits again, because a converging series is also a limit. So we have the sum and difference, we have the constant multiple, and we can use those to figure these sums out. So on this one, because this is almost identical to the harmonic series. Remember in the last video, I talked about the harmonic series was k equals 1 to infinity 1 over k. So it starts with 1, and then you add 1 over 2, 1 over 3, 1 over 4, and so on and so on. And that series diverged. Well, this starts at 4, but it's the same series after that. And so it's only missing the first 3 terms. So that series is still going to diverge. So since this is almost identical to the harmonic series, which diverges, this series also diverges. Same thing with 2 over k. Because we're using the constant multiple rule. So we still have a harmonic series, and then we have a harmonic series times 2. So since the harmonic series diverges, that series is also going to diverge. And then this one is a sum of 2 geometric series. So in this one, if they converge, we actually can find the sum because we have that formula for the geometric series that we learned about in the last video. So this one, R is 2. So our series converges because R is bigger than 1. And so we have 1A was 1 over 1 minus R. Our A is 1/2, R is 1/2, I'm sorry. When we put it in the R form, like you saw in the other examples back in the other video. And here R is 1/3, which is less than 1, so that geometric series also converges, and that becomes 1 over 1 minus 1/3. And so our sum is going to be, we have 1 over 1/2, which is 2. We have 1 over 2/3, which is 3/2, and that adds together to give us 7/2. So again, we can only find that sum because we have a formula for a geometric series. So in general, an infinite series converges only if the partial sums are bounded, and they have to either, the sum of an infinite series cannot exceed an upper bound. So if the partial sequence of partial sums is bounded, that means there's an upper and lower bound. Or it means that if it's an increasing function, it has an upper bound. If it's a decreasing function, there's a lower bound. So what that means is that you're continuing on to a certain number. And if a function is continuous, positive, and non-increasing on an interval, so if it's not continuing to increase, then we can use what's called the integral test. And the integral test uses an improper integral. And the improper integral will show whether the series converges or diverges based on whether there's a limit. That limit exists when we do this improper integral, or if it does not. So in this first one, we're going to use f of x is 4 over k squared, or x squared plus 1. Okay, that's going to be our f of x. We're going to plug in x instead of k there. And so then we know that on the interval that this particular function is continuous because there is a value for every x in that domain. Positive, because when we plug in any x in that domain, we get a positive answer. And non-increasing, in fact decreasing. And we can show that it's decreasing because the derivative of that function, if we use the quotient rule, gives us negative 8x over x squared plus 1 squared. And that is less than 0 on that interval. So because the derivative is less than 0 on that interval, the function is decreasing. So we have to set up the conditions to be able to use the integral test. But once we know this is true, that the function is continuous, positive, and decreasing, then we can set up the integral. So we say 1 to infinity, we're doing an improper integral, 4 over x squared plus 1 dx. Then to do the improper integral, remember that we change this to the limit as b approaches infinity and make this 1 to b. And then we integrate like we learned way back in chapter 8. So hopefully you recognize that we have a constant multiple rule here where we could pull out that 4, and this is inverse tangent. So that gives us inverse tangent of x 1 to b. So then we have the limit as b approaches infinity for tangent of b minus the limit, or tangent of 1, and tangent of 1, inverse tangent of 1, sorry. You're asking yourself, where is tangent equal to 1? And that would be pi over 4. Now for the infinity part, we have to remember the interval for inverse tangent. And an inverse tangent's interval is -2 pi over 2 to pi over 2. Remember with inverse trig, we had to set intervals or they wouldn't be functions because they would just keep going one on top of each other. And so since tangents period goes between -pi over 2 and pi over 2, they set that as the interval for the domain for tangent. And so inverse tangent for inverse tangent. So inverse tangent as it goes to infinity is approaching pi over 2. So we have pi over 2 minus pi over 4. And then don't forget that there was that 4 that we pulled out. And that simplifies to pi. Since now notice that converges to a number. So therefore we know that our series converges. That was the original question. Be very aware that this is not the sum. Okay, all we're doing is looking, does the improper integral converge to a number? If it does, then the series converges, but we don't know what the sum is. Okay, we'd have to find another way to find that sum, if it's even possible to find that sum. So most of the time, the sum of the series and that number you get when you evaluate the improper integral are not the same thing. So be very aware that that is not the sum. All right, again, use the integral test here. We're gonna first, you would have to show, which I'm not gonna write down, that 2x over x squared plus 1 is continuous, positive, and non-increasing. And again, you can do all of that. We can talk about it. It has to be on that interval 1 to infinity. So you can do all that. We can see it's continuous because you can plug in any value between 1 and infinity. Same thing for positive. When you plug in any value from 1 to infinity, you get a positive answer. And then the non-increasing, you can show it's a decreasing function because of the derivative. So just like we did in the last example. Once you've shown that, you have the conditions to use the integral test. This time, this is not an inverse tangent. This is a U substitution problem. So our U is going to be x squared plus 1. Our du is then 2x dx. So our dx is du over 2x. So just like we've always done with U substitution, we're going to substitute in, and I'm going to change the limits of integration. Because b is going to infinity, it's going to stay b, but when I plug 1 in for x here, I get 2. So now that changes that to 2. This was u, and dx is du over 2x, so the 2x's cancel. I get du over u, which is the natural log function. So I end up with the limit as b approaches infinity of the natural log of u evaluated at b and at 2. So then that gives me the limit as b approaches infinity, natural log of b minus the natural log of 2. Because that's infinity, okay, as b goes to infinity, the natural log of infinity goes to infinity, so this diverges. Okay, it does not, we don't get a number when we evaluate this improper integral, and therefore we know that that series diverges. Okay, this one looks complicated, but again, one of the things that you have to notice here is we're now on the interval 2 to infinity. The reason it's 2 to infinity is because if you plug in 1 for k, you get 0, and that does not exist. That series, there's no term when you plug in 1. So we're starting at 2 here, so that's important. So when we write our improper integral is going to be written with 2. Once again, you would show that this was continuous, positive and decreasing, which you can do. And then we have 2 to infinity, 1 over x, natural log of x squared. This is also a U substitution problem. If you'll notice, the derivative of natural log of x is 1 over x, so we have the derivative here. So we have that U substitution pattern, where u is natural log of x, and du is 1 over x dx, so dx is x times du. Okay, this time still infinity, because natural log of infinity is infinity. So that's still b. And then this one's going to be the natural log of 2 instead of 2. Then we have 1 over x, and then u squared, and then x, or dx, is now x du. So the x's cancel. So we have du over u squared. This is a power rule, where we have u to the negative 2. So that gives us the limit as b approaches infinity, negative 1 u to the negative 1 power, or negative 1 over u, evaluated at b and natural log of 2. So this one we're minusing negative 1 over natural log of 2, so I'm going to change that to a plus here. In this one, as b approaches infinity, this piece right here approaches 0. And so now we do get a number. And so again, that's not the sum. All this does is tell us that the series converges, because we do get a number when we evaluate that improper integral. All right, so the integral test is one that you can use on a lot of series to check to see. We have this new series now called a p-series, and we can actually use the integral test in order to prove the conditions of a p-series and how we know whether a p-series is going to converge or diverge. So you'll notice that a p-series looks like the harmonic series, and the harmonic series is actually a special type of p-series. So sometimes you're going to hear p-series called hyperharmonic series, because a p-series would be our harmonic series is a special case of a p-series in which p equals 1. So here's our harmonic series, but then we can have all kinds of p-series where p can be any number as long as it's a positive real number. So these are all different examples of different p-series. So the idea here is if p is greater than 1, then a p-series will converge, and if p is less than or equal to 1 but bigger than 0, because p has to be a positive number, then the series will diverge. So that's something that you want to remember about p-series. However, we can use the integral test to show that. So let's start with the p equals 1. If p equals 1, that's a harmonic, and we already know that a harmonic series diverges. So that's this part right here for diverging. Now let's look if p is greater than 1. So if p is greater than 1, we have a positive continuous decreasing function on that integral 1 to infinity, so we can use the integral test. So then we say 1 to infinity of 1 over x to the p power dx. So that's the limit b approaches infinity, 1 to b. Well, that's the same thing as the limit b approaches infinity, 1 to b, x to the negative p. So we're going to use the power rule to evaluate this. And so when we use the power rule to evaluate this, we get the limit as b approaches infinity, 1 to p, or no, as we evaluate that. Okay, so when we've used the power rule on this, we add 1 to this and multiply by the reciprocal. So that's 1 over negative p plus 1, and then that's also the power is that negative p plus 1. That's the power rule, and we're evaluating that from 1 to infinity, or 1 to b. So then we can pull out that constant, and then I'm going to switch this around to make it 1 minus p instead of negative p plus 1. So we pull out that constant, and we are evaluating now just this 1 minus p from 1 to b. So if we have 1 minus infinity, that's going to be a very big negative number, which makes b become a very, very small number. So that makes, if p is greater than 1 here, that's going to make this part equal 0, right? Because we have any number, the limit as b approaches infinity, if p is greater than 1, okay, we're going to have a really big number to a negative power, and then that's going to be getting closer and closer to 0. So it converges. And if P is between 0 and 1, then this number is just getting bigger and bigger and bigger and bigger and bigger as B approaches infinity. And so if P is between zero and 1, we're going to diverge. So that's where those rules come from, okay? If P equals 1 or is between 0 and 1, we're diverging. And if P is greater than 1, we actually get that equal to 0, and so we are converging. All right, so we're going to use that rule then to analyze different P series to see if it's going to converge or diverge. So here, P is 3. Since P is greater than 1, we can say that that P series is going to converge. Here, P is 1/2, because 1/2 is between 0 and 1, diverges. That's all you have to do to analyze a P series. And then you can find the upper and lower bounds of a P series. So you can't find the actual sum, but you can find the two things that it's between, which gives you an idea about where the sum is. It doesn't tell you what the actual sum is, but it gives you an idea about what it is because we know two things that it's between. So again, P has to be greater than 1 for the series to converge, and if that's true, then the sum of that series is somewhere between 1 over P minus 1 and 1 plus 1 over P minus 1. That's how you're going to find that upper and lower bound. So here for this part, all I have to do is figure out what P is. So in part A, P equals 3, so we know it converges, first of all. And then we know it's going to be between 1 over P minus 1, so 3 minus 1, and 1 plus 1 over 3 minus 1. So that becomes 1/2. And then 1 plus 1/2, which is 3/2. So we don't know what the actual sum of that series is, but we know it's between 1/2 and 3/2. Part B, P is equal to pi. So again, greater than 1, converges. So it's 1 over pi minus 1. Okay, notice that this is 1 over k to the pi, so that's how we want to write it when we write it for the bound. And then that's going to be less than 1 plus 1 over 1 minus pi, or pi minus 1. And then we can leave it like that. So again, all this tells us is what are the lower and upper bounds. So we know about what the sum is, but we still don't know exactly what the sum is. And then the other way that we can get bounds for the sum of any convergent series. So that was only for a P series. The way we can do it for any convergent series is, as long as, again, we have it is a positive continuous decreasing function, is to use the integral test. And so the sum of that convergent series would be bound by whatever you evaluate here with the improper integral for the lower bound, and then we have to take the first term in the series and then add that to this number that we got over here. So we have to, again, determine, okay, this function right here is positive. We have 1 to infinity. So again, we're on this interval. That function is positive on that interval. It is decreasing on that interval. We can show that again with a derivative if we need to. And it's continuous on that interval because it has a derivative. So we are going to do the improper integral. 1 to infinity. 4 over x squared plus 1 dx. And that's going to be our lower bound. So to evaluate that, again, we see that we have inverse tangent except for that 4. So I'm going to pull out that 4. So we end up with 4 Remember, this is one I did in another example, so I'm just going to kind of skip ahead to this part. Tangent to the negative 1x evaluated from 1 to b. And then that gave us 4. And when we evaluated b with the limit as it goes to infinity for tangent, then we get pi over 2. That's the limit. Tangent, inverse tangent of 1 is pi over 4. And so that's going to give us pi when we evaluate that. And so our bounds are going to be pi for the lower bound. Then we have our series. The upper bound is going to be our first term. So when we plug 1 in for k, we get 4 over 2, which is just 2 plus pi. So again, we don't know what the actual sum of this series is, but it's between pi and 2 plus pi. So we can get a very close estimate of what that is.